title somewhere two-thirds of the top. But I wanted to start with a problem, the happy ending problem, that probably some of you are familiar with, but it makes a nice story. So, and to my mind, this is the beginning of discrete geometry. There are certainly much earlier works that one could cite as being discrete geometry, but the first time that, as far as I know, it was studied explicitly. This is an observation made by a Hungarian mathematician, Eszter Klein, as a student in the 1930s. She had observed that if you have 5 points in general position in the plane, so no 3 of them on a line, then there's always a quadrilateral made by 4 of them that's convex. And there's more than one way to prove this. I saw a recent proof on math overflow that involves an unitary argument, but it's easy to prove just by case analysis. So you can count the number of convex whole vertices that you have. And that number is 3, 4, or 5. If there are 4 convex hull vertices, then they're convex quadrilateral. And if there are 5, then there's lots of convex quadrilaterals, any 4 of them. So the only interesting case is when there's only 3 convex hull vertices. Then the convex hull is not a good choice for your convex quadrilateral. But in that case, because the points are in general position, the other 2 points must be in the interior of this triangle, forming a line that cuts across it and has 2 points on one side and 1 on the other. And in that case, the 2 points inside the triangle plus the side of the triangle that this line misses form a convex quadrilateral. So in all cases, there's a convex quadrilateral. 2 of Klein's close friends were Paul Erdős and Erdös and Szekeres, also both students at the same time. And they saw this result that Klein had observed and found a way to generalize it to higher n. So they published a paper in 1935 that actually has 2 proofs that for every k, there's a large enough n so that every n points in general position have a convex k-gon in them. One of those proofs, the n that you get is really large, but the other one is only 4 to the k. So they proved that every 4 to the k points, or actually this slightly more complicated formula involving binomial coefficients, if you have that many points in general position, you have a convex k-gon. So if you have 256 points in the plane, you get a convex quadrilateral, where Klein had only proved to be 5. But it generalizes. And I'm not sure on what evidence, what was known at the time seems fairly slim for this formula to be the one that they guessed, but they conjectured that actually it's not part of the k, it's more like the square root of that. So 2 to the n minus 2 plus 1 points are needed to ensure a convex k-gon. And they conjectured that. The problem is still open. I think the prize would go either to proving or disproving this exact formula. And we don't know. But so after Klein and Erdös and Szekeres married, and that's why that happy ending of theirs is why this is called the happy ending theorem. So I suspect that Erdös and Szekeres might have known some of the rest of what I'm going to show you at that time, because otherwise how would they have come up with this formula? But This comes from something that the same two people, Erdős and Szekeres, published on the same problem much later in 1960. They showed that actually this 2 to the n minus 2 plus 1, if that's true, that's not possible because there are sets of 2 to the n minus 2 points that don't have a convex quadrilateral in them. And one way to see this is to use this construction, which it's, if you count the points in this, this is Pascal's triangle. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. Those are the numbers in Pascal's triangle. So we have this Pascal's triangle of point sets, where every point set in this triangle is formed from the two above it to the left and the right by gluing them together to make a monotone chain. And so that means that the point set to the upper, well, on my right, your left, the left point set must be below and to the left of the right point set, but we spread it out far enough to the left so that every line through two left points goes above the right point set, and every line through two right points goes below the left point set. You just spread them far enough to the left, that will always happen. So we get these point sets, and what we can prove about these point sets is that they don't have certain special convex subsets in them. Not the size of the largest convex subset in general. We can also prove that. It's not quite what we want. But we can define a special convex set called a cup. It's convex upwards. What that means is just that it's the subset of a graph of a convex function. And if you look at the set in position n choose I in this Pascal's triangle, the set in the ith from the left in the nth row of the triangle, where in both cases you start counting from 0, then the largest cup in that has this nice size n minus I plus 1, and the largest cap has size I plus 1. So down this left diagonal, there are big cups, but no big caps. The biggest cap in that diagonal has size 2, but the biggest cup has size I. And then the same on the right, and it's intermediate in the middle. Basically, because if you look at the structure of how a cup or a cap has to fit within one of these, when you group these point sets into their two sides, if you make a cup on the left side, you can't get any points on the right side, and if you make a cup on the right side, you can only use 1 point on the left side. And so you get a recurrence that the largest cup is the size of the largest cup on the left, or the size of the largest cup on the right plus 1, and the same with the caps, and that gives you this proof. Okay? So, as I said, in 1960, Erdős and Szekeres proved that there exist sets of points of 2 to the k minus 2 that don't have a convex k on. And one way to construct this is this same gluing procedure, where you glue all of the point sets in one row of this Pascal's triangle together in left to right order, with this same property that you space them far enough apart so that the lines through pairs of points on the left go above and the lines through pairs of points on the right go below. And if you do this, and you look at what a convex subset can be in here, well, either they are a convex subset of one particular point set in that row, or they start out as a cap on one side and then have a sequence of point, 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 cup on the other side. And based on that structural decomposition of the convex subsets, you can prove that there is no convex k-gon because we know how big the caps and the cups are, and when you calculate how big they get when you put things together, you get this number k. So the sum of the binomial coefficients in a single row of Pascal's triangle is a power 2, and that's where we get these powers to choose from. So very pretty construction. And I don't know because they didn't say, but it wouldn't surprise me if they already had some hints of this construction in 1935 and just didn't write it down, because how would they get this nice formula otherwise? But maybe they're just very good at guessing formulas.
There's one less than a power of 2 number of points in that.
No. We've got 1, 2, 4, and 8.
There's
another point way over on the other side.
So isn't this construction what led them to conjecture the Tiger formula?
The type formula is in the 1935 paper, and they didn't publish this construction until 1960. So, I don't know. So you can obviously start thinking about algorithmic versions of this problem. We're computational geometers, right? So, as far as I know, the history of algorithms on this problem started with Kotal and Tukey in 1980, who described a dynamic programming algorithm for the problem. But it was somehow simplified and sped up by Erdős and Szekeres in '89. If you want to find the largest convex subset of a point set, you can do that by guessing what the bottom vertex of the point set is, the one with the smallest y-coordinate, and then finding the largest convex subset that has that as its bottom vertex. That seems more complicated, but it's actually simpler. Because if you fix a bottom vertex and look for the largest convex subset of the rest, you can apply a form of projective duality and turn that into a problem of finding the longest convex chain of line segments in a line arrangement. And then what this paper by Erdős and Szekeres from '89 was really about was how to sweep a line arrangement, how to pass through all the vertices and line segments of the arrangement and list them all in some consistent ordering in n squared time, which is optimal because that's the size of the arrangement, but only O of n space. And that was an improvement on previous arrangement sweeping algorithms that had an extra log factor in the time bound by using a priority queue to figure out what the next thing to sweep over would be. So they invented this topological sweeping technique that doesn't quite sweep the arrangement by a vertical left-right sweep line. It sweeps them by a topological line, but that looser sweep order lets them save a log in the running time. And this has many applications, but one of them is this problem of finding the largest convex subset, because once you fix a bottom vertex, it becomes an arrangement sweeping problem, so you do it n times, once for each possible choice of the bottom vertex. And that gives you an n cubed time O of n space algorithm for finding the largest convex subset. And this is actually, I think, where I first started looking at problems like this, because I had a paper in '92 and another one in '94 that was on some related problems of finding convex subsets, but not just optimizing the number of vertices, but maybe finding a convex subset that has few points inside it, criteria like that. And the same sort of dynamic programming techniques apply to that as well. So there's been a very recent breakthrough on the problem, and I'm not going to go into it in a lot of detail because I don't understand it in a lot of detail, but it's not that long a paper. By Erdős, recently published the following found that every 2 to the k plus little o of k, and Suk's little o of k is k to the 2/3 log of k, but he adds in a note at the end of his paper that someone else had improved that to o square root of k. So every 2 to the k plus little o of k points in general position have a convex k gone in them. And his proof strategy involves finding a cup or a cap. These red points in this diagram. In the diagram, they're a cap. So that when you draw these yellow regions around the vertices of the cup or the cap, each of them has a lot of points in them. And then we can use another related theorem in combinatorics, Dilworth's theorem, to show that inside each of these yellow regions, if we partially order these points by the inclusion of the triangles they make with the 2 red points on either end of their little yellow region. So for each blue point, you make a triangle of that blue point and 2 red points. And you partially order them by inclusion of triangles. Then we could either find a large chain in that ordering, and that's a sequence of triangles that all contain each other, or a large anti-chain, a sequence of triangles that all of the vertices of which are outside all the other triangles. And by gluing these chains or anti-chains together using some somewhat messy case analysis, it shows that you can find enough of them to make a nice convex polygon. So, unfortunately, that's still not good enough to resolve the 2 to the k minus 2 plus 1 conjecture. It's 2 to the k plus something else. And so Suk doesn't get the $500 prize. But it's big progress, and it means that if you turn it around and ask what is the largest convex k-gon that you can find in a subset of n points, we almost know the correct answer. It's log base 2 of n minus little o of log n. So we've got the right first order term, but there's still some lower order terms to be corrected. So big progress. Now for me, this happy ending problem, this problem of what is the largest convex polygon that you can find in a particular point set or in any point set of a given number of points, has 2 very interesting properties. It's monotone, and that's the monotone in the title of the talk. It's monotone, meaning if you take away points from your larger point set, you're not going to make the largest convex subset any bigger. It might stay the same size if you take away the points that aren't relevant for it, or it might get smaller, but it's not going to get bigger. And also this is invariant under certain perturbations of the point set. It doesn't depend on exactly where the points are, especially if they're in general position. You can wiggle them around and it won't change what the convex subsets are. It depends only on the order type of the points, on the relative orientations of triples of points. So if you take an ordered triple of 3 points from a point set, that triple of points can be clockwise, counterclockwise, or collinear. And that combinatorial information about each triple of points is all we need to know to determine where the convex subsets are. It doesn't depend on a precise geometry, just on this combinatorial structure. And so here's some motivation for why I think those are important properties. If you look at the corresponding properties in graph theory, the property in graph theory is monotonic in the same way under the removal of points. If it's a hereditary property, if it's something that's true of all induced subgraphs of something with the same property. And these are really, really important in graph theory. There's a huge industry devoted to these properties. So cliques and independent sets, the size of them, those are hereditary properties. The chromatic number of a graph, whether a graph is perfect, claw-free, or triangle-free. I mean, claw-free and triangle-free graphs are defined in terms of not having certain induced subgraphs. But perfect graphs and chordal graphs have other definitions, and yet they also can be characterized in terms of their induced subgraphs. So there's this big industry. It also relates very closely to algorithms, because then we can ask algorithmic questions like how efficiently can we recognize perfect graphs? And the induced subgraph characterization of perfect graphs is central to the fact that we have Tollman time algorithms for them. So why don't we have the same industry in discrete geometry? We should. And actually what I'm going to argue next is that we already do. There's actually many, many problems. The happy ending problem is not unique in this respect. There are many, many other problems that all have this same feel. They're all invariant under perturbations of the point set that don't change the order type, and they are all monotone. And so we can define many different properties and algorithms for these properties, and some people here, like have already been studying them. So we should study them more systematically. So here's one. These are not in any particular order. I have a sequence of slides of a lot of different problems of this type. So first one I'm listing, projective clustering. We were given a point set, and we would like to find as few lines as possible that cover all the points of the point set. This is an NP-complete problem. Pat and Stefan have a fixed parameter tractable algorithm for it. But if you try to approximate it using the greedy algorithm, you're only going to get a log factor, and this example point set is one that pulls the greedy algorithm, because what you should be doing to cover this point set is taking all the horizontal lines, but the greedy algorithm will instead be tricked into taking all of the vertical lines. There's a different log factor approximation based on epsilon nets that also, as far as we know, only gives a log factor. And there's, we would like a better approximation algorithm. One way to achieve that would be to prove that the epsilon nets that you get from this problem have size better than 1 over epsilon log of 1 over epsilon. That's also open. So there are interesting open problems here, quite a bit of study in algorithms on projective clustering. But this basic parameter, the number of lines needed to cover a given point set, is one of these monotone parameters. It depends only on the order type of the point set. And if you take away points, it doesn't increase the number of lines you need to cover the rest of them. Okay, so here's one of the older problems that does also appear in the works of Erdős, but was studied longer than that. The node 3 in line problem. If I give you an n by n grid, it's a chessboard. In fact, this problem was originally posed on a chessboard. So you have an 8 by 8 grid, the squares of a chessboard. You would like to place 16 pawns on that chessboard so that no 3 of them are in a line. And by a line, I don't just mean the horizontal and vertical lines of the grid or the diagonal lines of the grid. I mean any line. There should be no line through any 3 points. How many points in an n by n grid can we place in this way? Well, if you try it for small n, it's an interesting puzzle. It's not easy to find these configurations, but it seems like it's always possible to place exactly 2 endpoints, no 3 in a line. So you can place 6 points on a 3 by 3 grid, 8 points on a 4 by 4 grid, etc., etc., as I've shown here. And if you can place 2 endpoints, that's optimal, because even avoiding horizontal lines, you can only place 2 points on each row of the grid. So that gives you enough. And actually, if you compute how many different placements of 2 endpoints there are on an n by n grid, they seem to be growing exponentially. So there's a lot of solutions. But nevertheless, it is not known whether it is always possible to do that. In fact, it's been conjectured not. So Guy conjectured that there were at most 1.8 n points in an n by n grid that you could place in general position. And Erdős proved that you can get at least n. The construction it involves modular arithmetic. So to place almost n points on an n by n grid, what you do is you find a prime p that's close to n, but a little bit less than it. Or it could equal n in case n happens to be prime. And you choose the points on I squared, that's their x and y coordinates, x equals I, y equals I squared mod p. Use those coordinates, and basically the Zeus theorem tells you that you can't place, no 3 of those are on a line mod p, and therefore no 3 of them are on a line in the Euclidean plane. So, cute algebraic construction, which was improved by Paul and 3 co-authors in 1975 to 1.5n, but we don't know what the right constant should be. We don't know that it's not 2. So any bound less than 2n would be a big breakthrough in this problem. But the size of the largest general position subset is another of these monotone parameters. And we happen to be looking at grids, but you could ask the same question about many other concepts. There's been some interesting work by David Wood and co-authors, Balog and Sharmoshi, on point sets that don't have large general position subsets. If you look at a grid, it's got n squared points in it, but its largest general position subset is at most 2n, so that's much smaller. But one reason it's much smaller is that the grid has these long lines of points, any one of which can only contain a very small number of points. If you look at a point set such as the one I've depicted here, this is a projection of a high-dimensional hypercube with 3 points in each dimension. It doesn't have any long lines of points. The most points in any line of this configuration is 3, but yet it doesn't have it doesn't have linear size general position subconfigurations. The largest general position subset of this is little o of n, but only little o by a little bit. Payne and Wood showed that there always is a general position subset of size square root of n unless you have lines longer than square root of n. But Balog and Sharmoshi showed that there exist point sets that, like this one, have the property that there are no 4 points on a line, and yet their largest general position subsets are significantly smaller than that. So, some interesting recent work there. Another famous old problem. How many lines of 3 points or more can you form from a set of n points. The number of lines of more than 1 point. If you take a set of points, you count how many lines contain more than 2 points. That parameter is another of these monotone parameters. The number of points is known for all sufficiently large n by a fairly recent theorem of Green and Tau that I'm not going to go into any detail about because there was a very nice invited talk by Ben Green at Sausage 2015 explaining all this. But just point out, famous old problem, discrete geometry, monotone parameter. The number of onion layers in a point set. So if you take a point set, repeatedly remove the convex hull, remove the convex hull, remove the convex hull, you get a sequence of nested convex polygons. The number of those polygons is a monotone parameter. Computing them is an interesting algorithmic problem solved by Chazelle with an optimal n log n algorithm, and it's a monotone parameter. So here, this is something that I've been working on recently with Sariel Parkella and Gabriel Livash, because Sariel and his co-author Erdős proved that an n by n grid has, well, in this case, it looks like a linear number of convex layers, but it's actually bigger than that. The largest convex subset you can get in an n by n grid has size n to the 2/3. And so in order to get all of the points decomposed into convex layers, you need at least n to the 4/3 layers. But that turns out to be tight. An n by n grid has exactly data of, I don't know if the constant factor is known, but data of n to the 4/3 layers. And what we observed looking at animations of what happens when you take really large grid and shrink it like that, they already noticed in their 2013 paper that it seems to be the case that the inner layers of this are very close to circles. They shrink from this initial square shape to a circular cross-section before they vanish at the center of the grid. And that is a property that of converging to a circle that is true also of some continuous shrinking processes for curves. There are several of these known. They played an important role in the recent proof of the Poincare conjecture, but the one that's important in this problem is called the affine curve shortening flow. And what this process is you take a continuous smooth curve in the plane, and you let every point of that curve move perpendicularly to the curve with speed proportional to the cube root of the curvature. And if they move, there's a different and more famous process where they move proportionally to the curvature, but in the affine curve shortening flow, they move proportionally to the cube root. This process shrinks any curve to a point. It's invariant under affine transformations of the plane, that's why it's called affine. And it has the process that any curve shrinks to an elliptical cross-section before it shrinks to a point. Because it's affine invariant, you can't guarantee a circle. You could get any affine transformation of a circle, and so you get ellipses. And it seems to be the case that if you take any convex curve and you approximate it by looking at a very fine grid and taking the grid points inside that curve, and then you run the onion layer process on those grid points, you get a very accurate approximation to the affine curve shortening flow, but we can't prove it. So there are interesting things to be proven still about onion layers. Tukey depth, this is something that I worked on long ago, robust statistics. If you compute the centroid of a cloud of data points, the red cross there is the centroid of this cloud of data points. It can be thrown off by outliers, it can be very far from any of the actual points. If you compute instead the deepest point, measured by where the depth of a point is, how much of your cloud of data points you can cut off by half space, then that is a robust estimate. Even if you make many outliers, you're still going to get a point that's inside your cluster of data points. The deepest point anywhere in the plane for a cloud of data points is a good estimate of the central location of points, but unfortunately it's not invariant. We can change the order type of them. We can perturb some points, keep their order type the same, and get a different deepest point, a different depth of the deepest point. But if we look at the deepest point that belongs to the set of samples that we're starting from, then that is invariant and monotone. So there's some connections to robust statistics here. Whether a point set can be realized using integer coordinates is another monotone function. It's if a point set can be realized by integer coordinates, so can all of its subsets. There exist point sets, such as this one, that cannot be realized by integer coordinates. And Grunbaum asked whether this is the smallest one. But also open, we don't know how to tell whether a given point set can be realized by integer coordinates. It seems to be, it's plausible that it's hard for the existential theory of the rationals, but then that possibly wouldn't. There are problems of solving things by rationals. No, there are problems of solving things by integers that are undecidable. And it's not clear whether that might apply to this kind of problem as well. Instead of asking for coordinates that are rational or integer, we can ask for distances between all pairs of points that are rational or integers. There are a lot of nice ways of generating point sets that have all distances rational, but they end up with lots of points on circles. That's really the only way we know to make big point sets with all pairwise distances rational. And so I think it's a little misleading to call this the Erdős-Ulam conjecture, but that's what it's called, that there exists a dense subset of the plane in which all distances are rational. My impression from what they wrote is that at least Ulam didn't believe that this was true. He thought that this would be unreasonable to be true, but he did ask this question: does there exist a dense subset of the point for which all distances are rational? If that was the case, then we could draw every planar graph with its edges as straight line segments of integer lengths. And we don't know how to do that. The question of whether we can do that is known as Harborth's conjecture. And so there are some intermediate questions between the two that I think are very interesting. And here's one of them. Is there any general position subset of points in the plane that has no combinatorially equivalent integer realization? If there is such a general position point that can't be realized, then the Erdős-Ulam conjecture would be false. Because if there were a dense subset of the plane, we could use a subset of it to realize any finite general position set. On the other hand, if every general position subset can be realized with integer distances, then we could use it as a set of points to draw your favorite graph. Draw your favorite graph with general position points for its vertices, perturb it to be one of these equivalent rational distance realizations, expand it to make the rational numbers integers, and you have an integer flying with your favorite plane of graph. So if we could answer this red question, we could answer either one of these two famous conjectures. And again, rational distance realizability is monotone. There's a connection to Paths with low stabbing number, which is a problem that has been investigated a lot in range searching data structures. The minimum stabbing number of a path through a given set of points in the plane is a monotone parameter of those points. How many lines are needed to separate all points in a given set of points is closely related because the stabbing number is at least n over that number of lines, and therefore this set of points in a grid has no path with stabbing number better than square root of n because it has a small number of lines that can be used to separate it. And there's a very recent result of Sariel that I think is quite interesting that tells us that random points in the unit square are very different from a grid in the sense that they need a lot more lines to separate them. And I would like to talk about some of my own work here related to graph drawing. There's this question of universal point sets. A universal point set for the n-vertex planar graphs is a point set that can be used, some subset of it can be used to draw the vertices of any planar graph with straight line edges. So any planar straight line graph can be drawn with its vertices in an n by n grid, therefore the n by n grid is universal for n-vertex planar graphs. But it's not the best universal set that we know of. There are smaller universal point sets that are smaller only by a constant factor. There are universal point sets for n-vertex planar graphs that have size n squared over 4, and that's the best we know. On the other hand, the lower bounds that we know for the size of universal point sets are they're linear, but with a constant factor only slightly better than 1. So there's a big gap there in our knowledge that we'd like to close. But this question of whether we can draw all planar graphs up to a certain size, what is the largest size k such that we can draw all k-vertex planar graphs on a given point set, is another of these monotone parameters. So again, it fits into the same collection of results. Now, I've given you a big catalog of these parameters that are monotone and invariant, and if we look at them as a collective, what does this perspective give us? So every time we have a monotone parameter, we can characterize it in terms of its obstacles, the smallest point sets that could exist inside a point set and prevent it from having a small parameter value. So these particular point sets are among the obstacles to, for instance, the property of being able to be covered by 2 lines. If you have any of these point sets in your input cannot be covered by 2 lines, and they're minimal with that property. They're not quite the only obstacles, but so what that means is that one could compute whether you have that bounded parameter value. Are you coverable by 2 lines or not? Simply by a mechanical procedure of looking for those obstacles. We can go the other direction. If we have a finite set of point sets that we want to use as obstacles, we can look for the largest obstacle avoiding set. That's, for instance, the largest general position subset is of that flavor. We can look for the fewest points that we can delete to eliminate all the obstacles. We can look for a partition into obstacle avoiding subsets. That's the projective clustering problem. And so this gives us a general way of defining monotone parameters from these obstacles. Unfortunately, finding an obstacle is a hard problem. Testing whether a given set of endpoints include a particular subset as in an order type preserving way is an NP-complete problem. It's not fixed count parameter tractable. It requires an amount of time that is where the exponent is depends on k. The best I can prove is that it requires n to the square root of k time, but the best upper bound I know is that it takes n to the k time. So there's a gap there, but basically because you can encode the problem of finding cliques and graphs into this problem. But when you have a finite number of obstacles, it's polynomial, n to the k. The number of points that you need to delete from a given point set in order to reach a subset that avoids all of a given finite set of obstacles is fixed parameter tractable for a fixed set of obstacles, not changing, but where the parameter is the number of points you're going to delete. That's a fixed parameter tractable problem. And there's a really nice, actually it's an instance of a more general problem of hitting sets of bounded size that has been studied, among others, by Plum and Grohan, and can be solved using the sunflower theorem, which I think also has Erdős associated with it. Basically, you can find, if there's a lot of instances of your obstacles in your point set, you can find one of these sunflowers, which is a collection of obstacles that intersect in a very controlled way, and that allows you to find a kernelization for this problem. We can prove that this partition into general position subsets problem is NP-complete. And this is a diagram of the NP-complete proof. But we now know all sorts of other parameters that are monotone, and we can think about using them as the parameters for fixed parameter tractable algorithms. So partition into general position subsets, while it's NP-complete for its natural parameter, it turns out to be fixed parameter tractable for point sets that it can be covered by a small number of lines, which I think is a quite powerful parameter to use for this sort of problem. Property testing. Does a point set have a property, or is it very far from having a property? In the sense that you can delete a lot of, in order to reach the property, you need to delete a constant fraction of the points. It turns out that whenever you have finitely many obstacles, you also have a property testing algorithm. So for instance, testing whether a point set is in convex position. You could do it by computing the convex hull, but it turns out if you sample O of n to the 3/4 point and compute their convex hull and test whether they're in convex position, that is a property testing algorithm. Either they are, in which case you answer correctly yes, or if the whole point set is not in convex position, if the whole point set is far from being in convex position, then a sample of n to the 3/4 of them is likely to also not be in convex position. And the diagram here shows an example of a class of point sets that shows that your sample size needs to be at least n to the 2/3 for this problem. So there's a big automatically existing family of property testing algorithms for these problems. Unfortunately, there do not always exist finite sets of obstacles. The diagram here shows the first three in an infinite family of point sets, none of which is a subset of the others. So there exist infinite, incomparable sets of point sets, and any infinite or finite subset of this infinite family can be the set of obstacles for something. But then it's interesting to determine for each of these monotone parameters whether they do or do not have finitely many obstacles. And I think this is actually my last slide, but now that we have all of these different monotone parameters, we can start comparing them and building a big diagram of how they relate to each other. Which ones are the bigger ones, which ones are the smaller ones, which ones cause the point sets that have bounded parameter values to be well quasi-ordered, etc. And so this is kind of a roadmap to this big picture of all of the different parameters within an STP. So, as I've said already, I think this framework of looking at monotone parameters that depend only on the order type, it unifies many famous problems in discrete geometry, and it gives us new algorithmic insights based on this characterization of these properties by their forbidden subconfigurations. And we get new exact algorithms, new parameterized algorithms, approximation algorithms, property testing algorithms, etc. So I think there's a lot more to do in this area, a lot of interesting open problems, and so I would encourage you all to be looking. I'll stop there.
Okay, thank you, David. Are there questions?
Your roadmap slide.
Yeah.
Is that available somewhere?
I will put these slides on. They include this roadmap.
Have you read anything about this?
Oh, okay. So yeah, I was intending to say this. If you look in the conference proceedings, you will only see a short abstract. When I got the idea to give this talk last November or December, I started writing a survey paper in December to be included in the proceedings for this talk, and it kind of grew. So I now have a 250-page draft book and a book contract, and so this should all be appearing in there in probably a year or so. Good.
The affine curve shortening flow, does that generalize to 3D grids and higher dimensional grids? It goes to an ellipsoid?
I don't know if the affine flow specifically has been generalized. There are flows in 3D. The complication is in 3D there's more than one kind of curvature. But there are flows in 3D that people have studied. Certainly people have studied the generalizations of the curve shortening flow, the one that moves linearly with respect to the curvature. But it doesn't behave anywhere nearly as nicely in 3D. In 2D, both of these flows, the curve shortening flow and the affine curve shortening flow, can never cause a curve to self-intersect. If it starts out being a simple curve, it stays a simple curve forever until it shrinks to a point. In 3D, that's not true. You can get things that pinch off.
Another question, is there, for non-monotone properties, is there any implication that things are more difficult then? So I'm thinking, for example, of empty convex polygons, where that would not be monotone.
Yeah.
You would remove a point and you get a bigger empty set.
Right, and so you can't characterize those necessarily by their obstacles, but yeah, that's obvious. I've written about empty convex polygons before, so that is definitely something interesting. But I didn't really have a lot to say about it with respect to these topics. So for instance, I'll just throw this out. You could start talking about first order properties of point sets, which would be properties that you can define using the first order formula with a predicate based on order type comparisons of triples. And I would like it to be true, and maybe it is true, that there's a 0-1 law for first order properties, that if you take large random subsets from a Gaussian distribution, for instance, that any first order property converges to have probability 0 or 1 of having that property. I don't know about that.
there any other questions? Not, then let's think.